So in terms of determining probabilities, we have to have either some kind of experimental study or some observational study. An observational study could be just a survey or just people going to different places to collect information. So here I have a relatively simple one. And Mother's Day is coming up. It's less than a month away. Most of us have mothers around. My mother's still alive. And this was some data, I think it was last year from the US Census Bureau, that if we look at the if we look at women between ages 15 and 50, how many of them have children at all? So 1 child, 2 children, 3 or more, or how many have no children? So as of last year, the Census Bureau data, again, women aged 15 to 50, 44% of them did not have children. So if we were like randomly pick a woman between 15 and 50, what's the probability that she would have no children? And according to this data, it's a 44% chance that if we randomly choose a woman between 15 and 50, she will not have children.
That's crazy. I thought it'd be way less than that. For
the, women, that is an interesting statistic. And I can't remember, let's see, it's been a while since I've looked at this one. Yeah, so they didn't give a lot of details here. They just gave a little bit. And then they had a further age breakdown just for first-time mothers and what the age distribution of was first-time mothers. And everything the Census Bureau posts, there's more details somewhere. You just got to dig to find it. But I thought this was some interesting bit of statistics from them. So let me share that out to anyone in case you're curious. So this is the Mother's Day, Mother's data. Screenshot that and ask a couple more questions about it. So for example, the first question I thought about looking at this right here is the probability that a randomly, and the random selection is important, randomly selected woman 15 to 50 years old has no children. So we might say something like probability children equals 0, like a shorthand for that. That would be 44%. Different question. What would the probability be? A randomly selected woman and again, this data only relates to women 15 to 50, so my mom isn't one of these women, has children. You think the answer to that one would be?
%46? When you just add these other percentages up for columns 1, 2, and 3?
Let's see. 10, 20, 30, 40, 56%, which should be the leftover from 44. So if we think about 100, so there's a couple ways to think about this question. One thing I could say is, well, if we take 100% and we subtract the 40%, 44% from above, right? Because this was no children, this is having children, and those are opposite ideas. That gives me 56%. Or I could add up these other probabilities, right? 17% plus 22% plus 17%. And again, that should give me 56%. Now, sometimes in tables and charts like this, there'll be a little bit of rounding error. These come out nice. They happen to work out to 100% total for all possibilities, right? Because a woman can either have 0, 1, 2, or 3 or more, right? There aren't any other options. So we should have 100% of women when we look at all possibilities. And that's another important feature of probability. That all the possibilities has to be 100%. Now, this idea of having no children, this one right here, versus having some children, these two different situations are called complementary events. And complementary in this case doesn't mean not complement with an I, meaning, wow, you've got some good looking kids there. It means they make a whole, right? My wife complements me. Together we make a good couple. So the idea of complementary events is, so the probability of no children relates to two different events versus the probability of some children right? Those things together add up to 100%. Anytime we have a situation like that where there's two situations, they make all possible outcomes 100%. Those are called complementary events. And we can use them because sometimes they can help us answer questions. So for me, easier than adding 17 plus 22 plus 17, I just thought, what's 100 minus 44? And I got the 56 because I realized having some children was the opposite of having no children. So in my head, I was thinking the probability of some children was equal to 1 minus the probability of having no children. And sometimes it's just an easier question when you look at it the other way. What's the opposite of this question? Is that easier to answer? If it is, then do that way and then just do 1 minus to get the other probability. Sometimes we kind of draw, there's some other kinds of pictures we draw of these called Venn diagrams, and I'll draw these sometimes when I'm trying to figure out probabilities. And so a Venn diagram, we have a square that represents everything, and then inside here we have some subset, like this subset right here might be the no children. And everything outside of that would be the opposite of no children, which is having children. And so we'll look at some Venn diagrams for some other situations. Okay, so again, big idea here, complementary events.
I always thought the Venn diagrams were always circles. I never thought of using them in with a rectangle.
Yeah, there's lots of different uses for Venn diagrams, and often I use them as just kind of when I have different groups that might interact, I sometimes will draw a Venn diagram to help me sort out how they're related, and we'll definitely do that today. So, next idea.